its specific equilibria. Okay. So not as math heavy as the chapter that preceded it, but certainly has a math component, but it's all just divisions. Okay. So in all, there's going to be 3 entire chapters on equilibrium in this textbook. 15, 16, and 17. We are anticipating spending 4 whole class times on this. It's going to be a fairly big deal. You may even run more than 4. Okay, so one of the things that people get wrong about reactions that are in equilibrium is they think that it's just reversible, that you can take reactants and convert them into products, and then take those products and convert them back into reactants. So the first misconception is this reaction is capable of going entirely to the right, and then should I do something about that to go entirely back to the left? Not to say that this reaction cannot proceed to completion, but the fact that we're even talking about it being in equilibrium tells us that it's probably not the case. The other thing that people get a misconception about is that the equilibrium lives in the middle. This is a reaction in which reactants have half of them have turned into products. Nope. Doesn't have to be halfway. It can be, an equilibrium position can be almost all the way over here, or it can be very, very little reactant actually gets converted into product at all. And we have a way of quantifying that. We're going to find a number given symbol K for the equilibrium constant. And then a third misconception would be that there are some reactants and they turn into products, and when you meet that special number given by the equilibrium constant K, the reaction stops. But the reaction doesn't actually stop. What the reaction does is churn. That we're going to get to a point, and then for every reactant that gets converted into product, product gets converted back into reactants. And so we have this situation where there is an exchange between reactants and products, but the overall quotient, the ratio of product to reactant, no longer changes. So this is a dynamic process. It's a dynamic process in which reactants and products are constantly being interconverted, but the outcome of that is that the ratio of products to reactants doesn't change. if I had a reaction, and the book actually doesn't even give kind of a symbolic reaction, it just leads off with the real one. What's happening here is that if I have reactants changing into product, and that reaction comes to equilibrium, which we show by the two-sided arrow, then we can call this reaction forward, and we can call this reaction reverse. Keep it really, really simple. Just A and B, just symbolically. Okay. So, what we learned from kinetics in the previous chapter was that we could write a rate law if the step from A to B was an elemental step, an elementary step. We could write the rate law for that based on what's on the page. That the rate would be equal to some proportionality constants times the concentration only of the reactants. So the forward reaction would be equal to the rate of the forward reaction is equal to the rate constant, that's a lowercase k, for the forward reaction times only the reactant of the forward reaction. And the rate of the reverse reaction would turn B back into A, coming this way, and that rate would equal its own rate constant times its own reactance, and B is the thing that's turning back. Okay? Well, at equilibrium, the rate forward is equal to the rate in reverse. Both of those reactions are occurring, but they're both occurring at the same time and at the same rate. So this equals that. The two rates are the same, therefore K forward equals KR. So and if I wanted to rearrange that, what I can do is just put the forward over the reverse. This A, we're going to keep the equal sign where it is. Going to move this K over to this side, so it will go underneath this KF, and I'm going to move that over here. So the ratio of rate constants gets to be the ratio of the species that are in solution. Now, which way did we write it down in the first place? Because we had gotten into the convention of writing our reactants on the left and our products on the right. So this has to stay as our convention. Reactants on the left, product on the right. But the equilibrium arrow says this reaction can go forwards or backwards. So at some point, it's not important. We can write that equation backwards. That's okay. These numbers will just flip. Okay? So this ratio right here of these two rates is going to be my new constant, and it's going to describe this equilibrium. So this is the thing that we need to know overall. K, that's now a capital K. And K is our equilibrium constant. You could abbreviate equilibrium as EQ and then superscripted M. The value of K can describe the forward reaction or the backward reaction, but because we have a convention that says reactants are on the left, products are on the right, the value of K expresses the equation the way that you have written it, which means the concentration of the products is on the top and the concentration of reactants is on the bottom. Okay, if we do a real life example of that, and there's a nice one in the book, that's what I was gazing at a second ago, because I don't have a nice one in my own lecture notes. There is an equilibrium. It's quite a good one. We'll not study it in our lab, but it is one of those equilibria that is studied in lab quite easily. That there are two nitrogen oxides that coexist in equilibrium and a condition as simple as the temperature will switch which side of this reaction you're on. And this one is brown, this is dinitrogen tetroxide, and this one is 2 molecules of nitrogen dioxide. So, nitrogen. It's really tetraoxide, but we don't like that combination of vowels. And then this is nitrogen dioxide. It's barely perceptible, but there is a space right there. Okay. So if we just did what we did by using the information that we already know, because we just did an entire week on kinetics, that the rate of the forward reaction is equal to lowercase k, the rate constant for the forward reaction, and my only reactant is N2O4. And in kinetics, you only concern yourself with the concentration of the reactants, because in kinetics, the products haven't been made yet, so they cannot, the products haven't been made yet, so they cannot affect how fast the rate of making them is. They can affect things like how much energy is given out or taken in. They can affect the thermodynamics, but they're not going to affect speed. And then the rate of the reverse. Tell me what the rate of the rate law for the reverse reaction is. assuming that the forward step and the reverse step are both elementary steps. And in an elementary step, we look at the molecularity in that step, and we can write the rate law based exclusively on what the reactants in that step are. What should be the rate law coming back? Rate equals K, reverse, times what? Anything else? Squared. So the kinetics of the elementary steps tells me that the forward reaction was what type of reaction? Forward one is first order, there's only one reactant in it. But the reverse reaction contains two molecules of reactants, and therefore the reverse reaction is second order. I'm going to mix those. I'm just going to put them on top of each other. So my value of K for this is the concentration of the products divided by the concentration of reactants and my value of K is, well, my products it's the reverse rate law divided by the forward rate law. Concentration of products raised to the power of their coefficients in the chemical formula. Okay? All right, let's invent a reaction that's got lots of moving parts and then write its value of K. Not its value, its description. We won't do numbers just yet. Numbers are going to appear soon. Okay, so for any reaction, got to be in equilibrium. A is a reactant. It's going to react with B. Can you see the spaces that I've left behind between them? That's for a reason. It's going to react together and make some C and some D. How many molecules of A are going to react? A molecules of A are going to react. How many molecules of B are going to react? B. And they're going to make C molecules of C and D molecules of D. So A, lowercase a, B, C, and D are our coefficients that describe the stoichiometry. They describe the mole ratios. Okay? K, uppercase. We have two Ks, little k, big K. Big K is for equilibrium. Lowercase k is for rates, for kinetics. It's always products over reactants. There's a reason that I've written this same line down 3 times already in the first few minutes of the class. This is something that you need to ingrain into yourself. K is products divided by reactants. It's going to tell us our forward progress. How far to the right has my reaction moved? Products over reactants. If we put the reactants on top, it would not tell us how far we have progressed in our reaction. Reactions are written with the reactants on the left and the products on the right. Okay, so for this particular reaction, A is my reactant. It will have a quantifiable concentration. Square brackets means concentration. Raised to the power of A. And multiply that by B, raised to the power of B. And then on the bottom, I have a concentration of this reactant, C. So concentration in the square brackets, C times D. Okay? This will be true of everything, except for the ones where we show you that it's not true, which will happen soon. It all starts out being true, and it never gets to be not true. What it gets to be is, there's a number in there that I don't need. So there's a little exception, but it's never not true. Okay, let's look at what some of these values of K will be. What do you think happens so here's my equilibrium, and reactant is turning into product, and K, fourth time I've done it now, got to be a reason for that. It must be important if he's written it out 4 times in a row. K is product divided by reactant. Yeah.
I have a question. So on that last one, where it was AB goes to CD,
Oh,
is CD the...
We do not propagate a myth or a mistake. What are my products? Thank you.
CZ.
C is my product. Raised to the power of C. I probably won't edit the video. I'm not a video. But yeah, here's me saying, there's a reason I've written it down 4 times in a row, dummies. Don't do it wrong, right? The product. Thank you. Wow. It is a Monday. Thank you. There's a life lesson right there. Somebody spots you making a mistake. Don't deny it. Own it. Accept it. Make sure everybody in the world knows it, and that this is what you really meant. Okay? Move on. That's what science is all about. Yeah, I didn't mean that, or yeah, I really did mean it, but thank you, you've proven me wrong. Being a scientist is quite a relaxing state of mind, because we're not, when it comes to arguing a point, it's okay if you prove us wrong. That's the whole point. You prove us wrong, you go, oh wow, I hadn't actually considered that. Great, now let's move on. That's how it happens, right? Or you make a dumb mistake. Products, C and D are products, raised to the power of the stoichiometric coefficients, blah, blah, blah. Okay, as the reactant gets converted into product, okay, in the scenario that the equilibrium position, remember the equilibrium position does not have to be in the middle. a dynamic equilibrium at which the reactants and the products settle upon some number that they are comfortable with. And there will be some interchange between reactants and products continuing, but we're done. Okay? Okay. Value of K right now is going to be big. Now, big is a ambiguous term. How big does big mean? We'll show you some real numbers in a second. I think I've got a couple written down. Okay. I've got a couple of real life. Okay, there you go. The breakdown of ozone. I got two ozones in the gas phase. So two ozones making 3 dioxygen molecules, and just like we saw with kinetics, where we had to quote a temperature when it, in terms of talking about the rate constant, we are going to need to quote a temperature when talking about the equilibrium constant. Let's write that down. So K. So our equilibrium description, the K expression for this. One more time. Products. This time I'm going to slow down. Products over reactants. Okay. The way that the reaction is written, these are my products. I have 3 molecules of oxygen, so that is an O2, concentration of O2 raised to the power of 3. And then underneath it, I'm going to have the concentration of my reactant, which in this case is ozone, O3, raised to the power of 2. The value for that is 2.54 times 10 to the 12. That's a big number. 10 to the 12 is a big number. That is 2, 5, 4. This would count as a 0. It's a big number. The knock-on effect of what we're seeing with K is that as reactants, if I take a little bit of reactant and I push it to be product, what I do is I take a number out of the denominator and I put it in the numerator. And when you divide 2 numbers into each other and you make the top number bigger, then your answer gets bigger. And when you make the bottom number smaller, then your answer gets bigger. And if you take a number out of the bottom and put it in the top, then your number gets bigger than you might have expected. Okay? Because it's not just I'm adding number to the numerator, I'm also removing numbers from the denominator. So the effect of moving a small amount of reactant from the left to the right has a big influence on the value of K. Big influence. So that's a fairly big number. Where's my other one? What do I do with it? Let's look at another one. Here is chlorine gas. And it's in equilibrium. It's a dissociation reaction. That a molecule of dichlorine gas can dissociate to be 2 atoms of chlorine gas. Yep, that can happen. And at 25 degrees Celsius, let's write the value of K. So the K expression is products. My product is chlorine atoms. 2 of them, raised to the power of 2. Divided by chlorine molecules. And the value of K right there is 1.48 times 10 to the negative 38. So that's kind of the workable range that we're dealing with. This would be 1 million. So that's 1,000, and then 1 million, and then 1 billion, and 1 trillion. The value for this K is 2.5 trillion. And then the value of this, we have yet to invent the descriptive number that says how small this is. Because 10 to the negative 3 is milli, 10 to the negative 6 is micro, 10 to the negative 9 is nano, 10 to the negative 12 is femto, or pico, and then 10 to the negative 15 is femto, and then I don't know what comes next. And we're not even halfway to describing how small this thing is. This is tiny. The equilibrium position for this is here. The equilibrium position for this one is there. Okay. What have we written down so far? Okay. All right. Don't need that. All right, let's see. Oh, I could do a little bit of graphing, because that's where the book goes next. Why not? So the book has a bit of a hang-up about the Haber process. It appeared in a couple of other chapters as well. The Haber process is very, very important, industrially massive reaction in which we take nitrogen, dinitrogen, which is a gas, and dihydrogen, which is a gas, and we make ammonia, which is a gas. And then we use that ammonia to make fertilizers. And that particular reaction is performed on a multi-million ton reaction scale every single day. Every single day there are factories churning out millions of tons of fertilizer because life is better with it than without it. We rely so completely heavily on factory agriculture that I don't think we would ever want to go back to the way that things used to be. Okay. Now that doesn't balance, first off. here's a clue. My reactants have 2 nitrogen atoms. We just do the straight atom count. My reactant has 2 nitrogens, but there's only 1 nitrogen atom in the product. And if your atom count imbalances, you should always multiply up, never divide down. So that means that my N2 has to generate 2 molecules of NH3. So now on the right I have 2 nitrogens. I have 2 nitrogens on the left, and I have 2 times 3 hydrogens. I have 6 hydrogens on the right, but I only have 2 hydrogen atoms on the left. So I put a 3 here. Okay. Now, wouldn't it be nice if just putting nitrogen and hydrogen in the same flask would generate ammonia? No. You need, from memory, I did my PhD on this, that the operating conditions here are 450 degrees Celsius and 150 atmospheres. Let's see if it's in the book. It says 500 and 200. There you go, it's about right. Very, very high energy consumption then, and you have to do this on a massive scale. This is not the only time that the Haber process is in this chapter. So it's in once on page 633, and then it comes back again somewhere else. Yeah, 651. They just can't get enough of it. Okay, so we're going to do this at very, very high temperature and high pressure, so it's going to require a lot of energy and make us this precious molecule that then we actually sell very cheaply. Products over reactants. What we'll do, I'm going to do 2 things. I'm going to write a little note to myself. I haven't currently enough examples on the board to go back and do the thing that I want to. Once I collect a number of examples on the board, I'm going to go back and do an aha moment. But let's look at this. If I plot, and the book has 2, I think they're doing concentration and rate. No, I know what they're doing. Yeah. Okay. If I plot concentration versus time, I might need some colors. I plot the concentration of ammonia versus time. We did this in the chapter on kinetics. Concentration versus time graph for ammonia. What does that look like? Ammonia is the product. It starts at nothing. At the beginning of the reaction, that's when there are more reactants floating around than anything else. So the chances of you making ammonia rapidly is going to be higher at the beginning. So we see a curve that does this. Saw that? Okay. Now, what happens to the concentration of of nitrogen. Nitrogen is a reactant, so it starts out high in concentration and then fades away. Now, if your reaction goes to completion, it fades away to nothing. This reaction doesn't go to completion. This reaction is going to get to a point and then go into steady state where the concentrations don't change. So I can make that a little bit straighter. It's going to be flat. Okay. We're going to make 2 moles of ammonia, and we're going to consume 1 mole of nitrogen to do it. So the nitrogen is going to start somewhere here, assuming this doesn't go all the way out to 2, and then it's going to drop off rapidly and go flat. And they should kind of flatten out at about the same place. Try and touch it up and make it better and make it worse. Okay, not unlike that. And then the hydrogen, brown doesn't look particularly good on this page, is way higher. And it's going to start somewhere up here and then drop. Now, quite where it ends up, don't know, but all of these things are going to flatten out, and at some point, right here, no, that's not quite right. You've reached equilibrium. So the concentration of the product has settled down. The concentration of the reactant has settled down. It declines. Reactants decline. Products increase. That reaction can read forwards or backwards, and therefore you could plot the backwards reaction of ammonia turning back into nitrogen. That graph would actually be a little bit cleaner, because we're certain of what we start with the 3 and the 1, 2 turning into 3 and 1. But at this point, all of those lines remain flat over time, if you just continue doing what you're doing. Things that would change it: temperature. Okay. So the thing that's staring us in the face that we haven't looked at yet is, I'm gonna need a little bit of space. What are the units for the equilibrium constant? Go back and work through some examples and see if we can spot what the units for the equilibrium constant are. What was the first one that we wrote down? We wrote down N2O4 turning into 2 molecules of NO2. So K equaled NO2 squared over N2O4. And K, the NO2 is measured in molarity. So we'd have moles per liter over the top squared divided by moles per liter once. So my answer would be in molarity. And what I've got here is molarity for the oxygen times 3 divided by molarity squared, which would tell me that the units are in molarity. I wouldn't write any of this down just yet. This might be a trap. Meaning, this is a trap. Don't write this down yet. That one has molarity squared divided by molarity. And this one has molarity squared on the top divided by molarity times molarity cubed. Oh. Yeah, funny, the first three examples, again, science, the first three examples seem to be opening a trend that reveals I have a trend. Units for the equilibrium constant are going to be molarity. Nope. What would the units be in this case? You have 2 on the top. It's like molarity times molarity on the top divided by molarity times molarity times molarity times molarity equals 1 over 2 molarities, which is 1 over molarity squared, which is molarity to the -2. Okay? Which tells me that the units for the equilibrium constants are going to change every time we look at a reaction. Even when we do something as harmless as say, that reaction goes forwards and backwards. What if I write it backwards? Now the units of my equilibrium constant change. So guess what we do? We do the good thing. We do the only smart thing that there is. We say that the equilibrium constant is unitless. It does not have units because there is no point at gazing into your navel that hard to try and figure out why the units are different every single time. Just tell me the number. The number describes the relationship. The relationship is then described by the magnitude of that number. The magnitude of the number tells me how far to the right I have moved or have not moved. Okay, I think a lot of the examples that we've written down so far have been in the gas phase. That's nice. Textbooks talk about gas phase reactions quite a lot because they're simple, some of them. But we never do any gas phase reactions in the lab because gases are very difficult to handle. That does not mean that fundamental work has not been done on this and will continue to be done on this. So what we need to do is look at what the relationship is. Should we want to measure a reaction in terms of gas or its concentration? Those two numbers are a little different from each other. If you measure measure the value of the equilibrium constant in terms of concentration, then your K now gets a subscript that says C for concentration. If, however, you measured the relative amount of product to reactant by measuring the pressures of reactant and product, then you have a number that is slightly different. That we would have the pressure of the product divided by the pressure of the reactant. So these two numbers are easily interconverted because what is our definition of concentration? Molarity. What is our definition of molarity?
Moles per liter.
Moles per liter. Moles, given symbol N, lowercase, volume, given symbol uppercase V. And if we quantified the V to be 1 liter, we now have molarity, not just concentration. Concentration is number of moles per unit volume. If you make that volume a liter, now you have molarity. Well, that's convenient because PV equals nRT. And there's an N and there's a V. So go ahead and rearrange PV equals nRT for me to read what N over V would be equal to. N is currently a numerator. V is currently a numerator. I want V to be a denominator. It's going to have to cross that equal sign, and when it crosses the equal sign, it will go to the bottom. That's going to leave the RT on this side that I don't want, so I'm going to pull it across the equal sign, and it will descend to the bottom. And N over V, therefore, equals P over RT. And this is in the book somewhere. Okay, so we can go and substitute N over V, or, hey, we can do it the other way. There's two ways of looking at it. Which way did I do it? Okay. So N over V is P over RT. So that will help me if I want to push the numbers this way. If I want to convert KCs right here into KPs, I would do that. If, however, I wanted to convert KPs into KCs, I might do this. Just move the V. If I do P equals N over V RT, this is the same as concentration right here. Okay. So if I have a reaction and I measure I find the value of k's this way with concentrations, I can push my numbers into here, P over RT's into there, or if I found my number in pressures, which is probably a more likely way to do it, then I can just replace those pressures with these and figure that out. Okay, so here's an example. Does this have numbers? I got a derivation here. I don't know that I want to bother. So we're going to have a conversion factor between the two. I don't think this is going to come up enough. I've got a little derivation that gets you there, that just puts n over v RT into any expression of this. So I'm going to put, and the coefficients of the reactants obviously is not going to change whether you used concentration or product. But then carrying those RTs through, they kind of get multiplied up. And you end up carrying through this term where the RTs are raised to a value that is the number of moles of gas products minus the number of moles of reactant. Okay. So it's just a manipulation of the numbers. I don't think we're going to do a couple of those. So we have planned for this afternoon in the math workshop. I've got a printout of the next problem set. There's two on that worksheet. One that I'll work through on the board with you, and one that I'll leave you to do for yourself. But it's not going to be a big deal. I don't have, there's a worked example in the book, or a calculation, there's no derivation. I don't know that it matters. Okay, so most of the K's that you see are going to be in that format. If it turns out that you have a table of these KC's derived from concentration, and then there's this odd guy, KP, right here, and you need it to fit in with the crowd, this gets to be your conversion factor. Okay. That's all. All right. Oh, I know what to do. Okay. So, did I put a I'll use this one. because it's up on the board. All right, so we write reactant on the left goes to product on the right. And this reaction is in equilibrium. So what if we said to you something kind of ambiguous? What if I said, write a balanced equation that describes the equilibrium between chlorine gas and its atoms in the gas phase? Didn't tell you whether that was an association or a dissociation. Didn't tell you which direction to write it. Doesn't matter. So the forward way, if I write chlorine molecule as a gas on the left and 2 chlorine atoms on the right, again, I'm going to have to, we'll get to temperature eventually. Factors that affect the value of K. K is absolutely going to be affected by temperature. Okay, so we've already written it down. The value of K is the concentration of the products raised to its stoichiometric power divided by concentration of the reactants. And because our convention has the reactants be on the left and the products be on the right, that means Cl squared divided by Cl2. And that number turned out to be a really, really puny number, 1.48 times 10 to the negative 38. What were the units? Doesn't have any, even though that's why they're written in red. Okay, so faced with ambiguous information, what if you wrote now, okay, still can you see what the mathematical relationship between those two might be? I'm not going to call them forward and reverse. Yes, I will. I have a value already of the forward reaction. The reverse is just this number upside down. It's just the inverse. You want to put a number to that? Break out your calculator and tell me what 1 over 1.48 times 10 to the negative 38 is.
.76 times 10 to the 37.
6 points. We have 3. 76 times 10 to the 37. Okay? Let's look at these numbers and rationalize what the values mean. Normally when we want to rationalize a number, we have to look at its units and its magnitude. There are no units. This is an infinitesimally small number. It tells me that the equilibrium position is somewhere here. That the number of product molecules in my equilibrium mix is tiny. Very, very small. But the reaction has gone so far and decided, I don't need to go any further. I've settled at this, at that temperature. We don't know exactly how it's going to respond to temperature in the future. Where on my reaction coordinate between reactants and products is the equilibrium position for this one going to live? Way here, over on the right, which is the same thing. It's the same thing. If I know that number, then I know this number. If I know this relationship, then I know that relationship.
How do you get the 1.48?
Oh, it was quoted to me.
Oh.
It's in a text somewhere.
Okay.
Okay. You can find it experimentally, and we'll do some calculations to show how to get it. What you have to do is you would have to measure the concentration of, because we're doing it this way, of the individual chlorine molecules and the individual chlorine atoms. So you'd have to have some method of detecting them away from each other, or measuring the pressure and then converting it to Kc. All right, one thing, then we'll take a break. Everything that we have seen up to this point has been pretty straightforward. There are examples of what we call homogeneous equilibrium. Plural of equilibrium is equilibria, not equilibriums. And a homogeneous equilibria is all reactant and product molecules are in the same phase. And I think just about everything that we've seen this morning, starting out with the easy ones, if the book shows you something in the gas phase, it wants to show you something fundamental, because it's just these bunches of atoms interacting with those bunches of atoms right there. There's no solution effects, there's no solvation, there's nothing getting in the way, there's diffusion. But it's at its simplest level. So this could be all gases. And we could measure P, or we could measure C. We could measure the pressure, measure the partial pressures of each of the individual gases in the reactant and the product, or we could measure their concentrations. Or they could be all solutions. At which point they wouldn't have anything other than concentration for us to measure. Okay. With the slight aside of, if you do measure in P, and then you want to change and compare that number Kp to Kc at somewhere else, then there is a conversion factor between Kc and Kp. It's just type RT to the raised to the power of delta n. Okay, let's look at a couple of exceptions. And here's what I was hinting at earlier. It's never going to be wrong, but there are cases that don't fit. So we have the possibility of having heterogeneous equilibrium. And the book gives one example, two examples. Okay, let's go elsewhere. Okay, let's start with something very, very straightforward. It's going to come back in the next chapter. Acids are things that when you dissolve them in solution increase the H plus ion concentration, and binary acids are often combinations of halogens like HCl, HBr, HI, and HF. Now where hydrochloric acid, hydrobromic acid, and hydroiodic acids are all strong acids, hydrofluoric acid, AQ in aqueous solution, is a weak acid. When it dissolves in water, it does not dissociate 100%. It forms an equilibrium. So I'm going to dissolve it in water. And it's going to give away its H plus and form a conjugate base, which is fluoride. Okay? Now, HF is in aqueous solution. H3O plus, the solvated hydronium ion, it's in aqueous solution. Fluoride is in aqueous solution. But water's a liquid. So these things are not all in the same phase. They're all in solution, but they're not in the same phase. K is product divided by reactant. The concentration of H plus in solution is something that we can measure quite readily. We've got pH electrodes that help us do it. We used one on Thursday in lab. Fluoride we can measure, and we can titrate to find the original value of HF. So we know that concentration, we can know this concentration, we can know that concentration. But the H2O, that's a liquid. And even though we may have done the problem the other day that says, what is the concentration of pure water? Doesn't fit here. Or one school of thought says it doesn't fit at all. The other school of thought says it is so massive at 55.5 molar that none of these piddly numbers are ever going to change it, and therefore it's constant and unchanging, and therefore we can ignore it. So when you write down an equilibrium expression and you know it's wrong, you mark it with a dash. So the K dash for this is this expression. The K, when you know to exclude something that doesn't matter, looks like this. Okay, let's take another look. What else have I got? This reaction is heterogeneous, but in equilibrium. This is calcium carbonate, which is limestone. When you heat it, it loses a molecule of carbon dioxide and leaves behind lime, calcium oxide. And that equilibrium position is reversible, but I have two solids in this phrase, so I'm going to put product over reactant. Okay. And then you take out the red pen and you say, that cannot be there. Because they're solids. And they're in the box marked concentration. Okay, what is concentration? Moles per liter. Okay, how many liters was your lump of chalk dissolved in? None. It's not a concentration. Solids don't have concentrations. So solids and liquids get removed because solids and liquids cannot have concentration. So solids and liquids are removed from our K expressions. Because they don't have concentrations. There is no concentration for a solid. There is no concentration for a liquid. There is concentration for solutions. Or there are pressures for gases. And so the K prime, you write that down because you know that you're doing it wrong, but you're including everything, and then you cross out what it is that you're not going to use. The K for this equilibrium is kind of small. All right, let's take a break. It's Monday morning. We can all do better. And we'll try after the break.